Chapter 11 is about liquids. Last chapter we talked about gases. And then what they call intermolecular forces. These are forces in between the molecules, not in the molecules. They're not a covalent bond or an ionic bond. Instead, in between the substances. Because remember, anytime you have a compound or an element, if you have 1 mole of that substance, you have Avogadro's number of molecules or atoms. That's a lot. So there's forces in between those guys that hold them together as well. Okay, an intermolecular force, if it's here you have an attraction between that positive, negative. This is a strong bond in the molecule, but in between the molecules, between these two, there's going to be a force in between them as well. Okay, so there's forces in the molecule and they're way stronger. Okay, the bonds in between the intermolecular forces are much weaker, but they're there and they give properties to liquids because of it. Okay, many of their physical properties is because of their intermolecular forces, like their boiling points and their melting points. The stronger the intermolecular, the higher the boiling point and the higher the melting. Viscosity, you can't see that one, sorry, we'll talk about that one. Surface tension and capillary. So these are caused by the forces in between the molecules, not in the molecules, but in between. Okay, remember we talked about states of matter and I said gases were way different, because if you look at liquids and solids, the particles really aren't that far apart. Okay, we will talk about solids. That's our last chapter we're going to cover. But liquids, you can see, are not much different. So these guys, solids and liquids, properties are much closer together than a gas. Okay, when we're talking about intermolecular forces, we're talking about in a solid and a liquid, not in a gas. All right, the gas, just the particles are too far for that to happen. Okay, and again, because the gases have that kinetic energy, it's not going to happen. But a liquid and a solid, they're kind of called the condensed forms, because you look how close these are. Now we have these intermolecular forces and they change the properties of the substances. Okay, again, looking at if you look at ionic bonds, metallic, and covalent, remember these are our 3 types of bonds. I know we didn't talk about metallic bonds, but they just occur between 2 metals. You can see that the melting points and boiling points, give you some information. And then it talks about dispersion force and dipole forces and hydrogen bonding. I'm going to talk about those different intermolecular forces. Okay, so these guys are chemical bonds, and you can see they have much higher numbers than the intermolecular forces. So in the molecule itself, the forces are much stronger than in between the molecules. So they're much weaker. Okay, and hydrogen bonds, when we say that, we're not talking about chemical bonds. Okay, we're talking in between. So an intermolecular attraction, it's not a bond. Okay, it's a force in between them, but it's not like when you're talking about a covalent bond and ionic bond. Those are actual bonds. These aren't. They're just forces in between. Okay, if we go weakest to strongest, the weakest is what they call dispersion forces. Okay, there are London dispersion. I don't know the difference between, but dispersion forces, there's just a natural attraction between them. They're induced and they don't have any charge. These are what happens in noble gases and non-polar covalent substances. This is the only force in them. It's a very weak force. Then there's what they call dipole to dipole. I mean, when you have polar bonds, you have a positive end and a negative end. The positive and negative of each side is going to be attracted to each other. Those are going to cause forces. And then there's hydrogen bonding. Now, hydrogen is a special dipole because hydrogen is so little. Its force, its intermolecular force, is stronger than a dipole. But the thing is, you have to have hydrogen in order for it to happen. Hydrogen is very common. It's in a lot of substances, but the only way you can have hydrogen bonding, which would be the strongest intermolecular force, is to actually have hydrogen. Okay, the first 2 are called van der Waals forces. They're always there, but again, they're not super strong. The dipole is by far stronger than the dispersion forces, but again, to have a dipole, you have to have either ionic substances or you have to have polar covalent. You have to have poles. Okay, so those are the forces. Things that affect their strength would be the number of electrons of an atom. Okay, the more electrons you have, the more force you have. The size of the atom, its weight. Okay, the more it weighs, the stronger the intermolecular forces. And the shape. Okay, if the molecules that have similar masses, they weigh about the same. And if they're more compact, if they're more, like these guys, if you compare a spherical to a linear, these guys are going to have more force between them than these guys. Okay, so things that can affect those dispersion, the number of electrons, the size of the atom or molecule, and the shapes. Those things affect how strong the intermolecular forces are between them. Okay, if it's a dipole, again, remember, you have to have either an ionic or a polar covalent, and mostly polar covalent, because you have to have poles. You have to have a positive end and a negative end. And the dipole exists, if you can see here, the blue is attracted to the white, or I guess it's the gray here. Okay, so the blue, gray, in between. Okay, so you have an and, a positive end. This white and gray is the positive end, and the blue is the negative end. So they're going to be attracted to each other. Okay, so they're going to form intermolecular forces in between them. And again, it's not as strong as a bond. Okay, but the opposite charged ends will be attracted to each other. And again, like in an ionic bond, you have your positive and your negative ions attracted. That's actually a bond, okay? But with these guys, this is in a polar covalent substance. They're going to have that force in between them. Okay? Hydrogen bonding is the strongest intermolecular force. But again, you have to have hydrogen. If you don't have hydrogen, it can't happen. The bond forms because hydrogen is such a little molecule. It ends up being very positive because everything else gets sucked over here to the negative end. So it's like a dipole on steroids. It has that extra kick because of it just having that positive end. Okay, the hydrogen bond is stronger than a dipole. They're very similar in the sense that the negative is attracted to the positive. Okay, so the hydrogen bond is attraction between hydrogen atoms attached to a highly electronegative atom. In other words, you can see oxygen's much more electronegative than hydrogen. So these guys, these are in between the molecules. This would be the strongest of them because fluorine is the most electronegative of all atoms. It's got the highest number. So again, but you get this bond being formed, and it formed and it's broken, it's formed, it's broken. It's just a force in between trying to hold them together. Okay? And again, it's like a dipole, just because it's hydrogen, it's stronger. Okay, well, what does it do? Because of these intermolecular forces, we have things that happen. Okay, one of the things that happens is if you compare ice to liquid water, and now every other substance, the solid is more dense than the liquid, right? I mean, metals, if you melt a metal, it's much less dense than if it's solid or whatever. But water is different because of these intermolecular forces. Water at 4 degrees is the most dense. Ice, if you can see the same amount, and then you've probably done this before, where it freezes. If you've ever had your pop freeze or whatever, I mean, why? If it was normal, like most things, it would get smaller and it shouldn't be a problem. But it doesn't. It actually expands. It's less dense. Well, that's not a big deal in your pop. Yeah, if it was, then your pop wouldn't explode or whatever. But what is really important is in lakes. Think about if ice was more dense than liquid water. Lakes would freeze from the bottom up. What would happen to all the fish? What would happen to everything that lives in the lake? Okay, for a couple days, you'd have really good fishing because all the fish would be on top until it froze. So it's really nice that ice floats so that you have your ice here and then you have your liquid water under here. Okay, I don't know if they, set it up that way, but that's the way it works. So hydrogen bonding makes the molecules farther apart in ice than in liquid. And again, water's most dense at 4 degrees Celsius. So when you go right underneath that ice, that water is going to be about 4 degrees, and then it gets a little bit warmer as you go down. But again, that prevents, we already have fish kills in the winter. This would really be serious fish kill. It would be every winter. Okay, so you get if you have an ionic compound, you also have dipole attractions. Here's water with chlorine. Water is a great solvent. It'll dissolve almost everything. It won't dissolve nonpolar substances like oils, organic compounds. But because of that ability of the positive and negative, it will pull apart ionic compounds. It will pull apart polar covalent compounds. So that's why water is such a great solvent, is because of those forces, those dipole forces in between. Okay, the strength of these forces is what makes it possible for ionic substances to dissolve in polar substances like water. And again, water is called the universal solvent. It will dissolve more things than anything else, and it's because it's a polar covalent substance. It has the ability to pull things apart because of its poles. Okay, so if we're going to look at generalizations about intermolecular forces, okay, when two molecules have the same molar mass or they're similar to each other, They're similar in shapes. Their dispersion forces are going to be about the same. Okay? The forces in between, again, are going to be about the same. Okay? When you have two molecules that have very different molecular masses, like one's huge and one isn't, or whatever, and if there's no hydrogen bonding, because hydrogen bonding changes those things, their dispersion forces determines how strong the attraction is. So here, these guys really aren't that much different, are they? Okay, each molecule can form a hydrogen bond with its neighbor, and then you'll get more attractive forces. So again, the closer they are to each other, the more likely they'll have a good force, a good bond, or not, I shouldn't say bond, a force between them. It's not a bond, okay? I want to say that, but it's not. Okay, so what things are affected in liquids by these intermolecular forces? First one is boiling point. Okay, the stronger the intermolecular forces, the more energy you have to boil it. Okay, the viscosity, we'll talk about that one. That's the resistance to being poured. Surface tension and capillary action. So we'll talk about those four things. Okay, and again, these are all because of the intermolecular forces in liquids. Okay, viscosity is the resistance to flow. Okay, you probably hear about this with oil. You obviously don't want your oil to be too thin, because if it is, then it doesn't protect your engine, and then you got all kinds of problems because of it. Okay, so the higher the number, the higher the viscosity. That's why we have higher numbers. We use 10W40 in the winter and 10W30 in the summer. In the winter, we want it to be heavier because, I said that backwards. In the summer, we want it to be heavier because it's already warm. You know, you want to protect those pistons. In the winter, we want it to be thinner because it gets cold and we want it to move. Okay, so we change our viscosity. And again, this is when you buy your oil, the numbers. You want the thin stuff in the winter and the thick stuff in the summer. Because again, in the summer, you already have that hot. So it's going to spread out anyway. So you want it to be thicker. In the winter, you don't have that hot, so you want it to be thinner. Okay, that's viscosity. And again, it relates to how easy it is for the molecules to move. The more viscous it is, the harder it is to pour. It's like comparing water to molasses. Molasses is way more viscous than water. They have stronger intermolecular forces. Okay, so the stronger the intermolecular forces, the more the viscosity increases. Okay, it's going to decrease at higher temperatures. And again, that's why in the summer you want it to be heavier, because the temperature is going to lighten it anyway. But in the winter, you want it to be lighter because the temperature is lower and it's going to be lower anyway. So with viscosity, that's its resistance to pour. Okay, here's surface tension. Surface tension is the thing you feel when you jump in the lake and you first hit that water, especially if you do a belly flop, that bam, there's like a skin on the water. And again, it's because the molecules on top are kind of attracted to each other. They have a force between them. If you're a bug, like this guy, you actually use that surface tension so you can cruise across it, okay? And what it does is it causes the water to bead up. I'm sure you've seen this on your windshield when it's raining. You know, you have a couple and then they kind of get together and whoop, down they go. But until they get enough of them together, they're not heavy enough and they'll stay and they'll bead up, okay? And that's surface tension, okay? So those are caused by intermolecular forces. And then there's something called cohesion and adhesion. They're intermolecular forces that bind similar molecules together, okay? So if they're the same molecule, it's really going to bond them together. But they bind, there's cohesive forces and then there's adhesive forces, okay? Intermolecular that bind a substance to a surface is adhesive. If it's below the surface, that's cohesive. I don't know why they get to have two different names, but if you look at it, cohesive and adhesive, they're really very similar, okay? They're important in what they call capillary action. Okay, capillary action, you guys have probably seen this if you have given blood and you prick your finger and they take some blood to check your hemoglobin and the blood actually goes up. Okay, the rise of the liquids is because those particles are attracted to each other, so they move on up. If the tube is small enough, they'll move on up. Okay, they are attracted to, the adhesive forces attract the liquid to the wall of the tube, and the cohesive forces keep the liquid attracted to itself, so it goes on up the tube. Okay, that's capillary action. And like I said, I'm sure you guys have seen this. We're just about out of time, so I'm going kind of quick here, sorry. Okay, so water has stronger adhesive forces with the glass. Mercury would have stronger cohesive forces with itself, and that would determine it. But again, they would work by capillary action. And that's all the time I have for this part of the chapter.